Hello, world. My name's Yuval, if you don't know me. I want to thank the organizers of this conference for doing such a great job of doing this online workshop. I've been really impressed with it so far. I'm also really appreciative that I get to follow Earl, because you get to see a lot of the work that we're avoiding in this talk. So the title of this work is Compilation of Fault-Tolerant Quantum Heuristics for Combinatorial Optimization. And this is work with a relatively large team. So there's me, I'm a postdoc of Dominic Berry, then the other members of the team here in Sydney are Pedro Costa, another postdoc of Dominic Berry, and Louis Tesler, who's a student of Dominic's. And then this is work that we did jointly with Nathan Wiebe, who's at Pacific Northwest National Lab and the University of Washington. And also there's a few people from Google on this one. So there's Craig Gidney, Hart McNevin, and Ryan Babush is really the leader on this. We have a paper on the archive, so you can take a look at the paper if you like. That's in small letters over there. And yeah, I'm coming to you from Sydney, so it's actually nighttime here. And also, because I'm in Sydney, we use British spelling, and you guys are in Cambridge, and you use British spelling. I will also use the correct spelling. So, that's apologies to the Americans, I suppose. So so just before I really begin the talk, I just want to make a certain point, which is that our paper is 77 pages, and the number of minutes that I'm allocated for this talk are 20, which is a very appropriate number, except that if I was to try and cover everything in this paper, this would be 3.85 pages per minute. So this is not realistic, so I have to make some judgments about what is being presented and what is not being presented. So my aim is essentially to give an overview of what the paper is about, and then some kind of a guidance about what you might find in this paper, so that then the hope is that you can go check out the paper for specific techniques and so on. But the overall message, I'm hoping, will be very clear from this talk. So the overview, so I like to start my talks by giving essentially the entire talk in one slide, and then essentially the rest of the talk is an elaboration on this slide. So the problem that we're looking at is combinatorial optimization, and we're interested in combinatorial optimization because this is a quite likely use case for quantum computers. And the current approaches to doing combinatorial optimization on a quantum computer suggests a quadratic speedup. Now, this is not to say that better than quadratic speedups could not be found, but these are the ones that we're aware of right now. And what we're interested in is asking whether an early quantum computer would actually beat classical computers, given that these are the sorts of speedups that we're talking about. And for the purposes of this talk, what I mean by an early quantum computer is something along the lines of what Google means by an early quantum computer. So this is roughly 1 million physical qubits with some level of error that seems appropriate for their hardware as they see it, and the errors are being corrected by a surface code. So I'm hoping people have seen these sorts of visions that Google has. This is about the most I'll say about the architecture, but this is sort of what you should have in mind. So, so given that we're actually asking to what extent an early computer would beat classical computers, and by early I do mean like sort of these 1 million physical qubits thing, nothing bigger than that, it does seem to be the case that the quadratic speedups aren't good enough for the quantum computers to beat classical computers. And that's probably not so surprising or concerning for people who really know the algorithm stuff, but it might be that people who aren't so closely connected with the algorithms are a bit surprised by this. I have a list of caveats to give, but the takeaway message that I would offer for this is to say that we should manage our expectations about whether the first, well, what Google would call the first fault-tolerant quantum computer, so for the purposes of this talk, I mean a non-NISQ quantum computer, we should just manage our expectations about how useful this first quantum computer would really be for combinatorial optimization. And some indications that I found was essentially that my laptop would beat the quantum computer in at least certain ways. So with those strong statements, there's a pile of asterisks that I should give. And these aren't all the asterisks I should give, but these are the main ones. So the first thing to know is that we are looking at heuristic methods. So we're not looking at methods that are guaranteed to return an answer. We are looking at methods that are sort of likely to do well under most circumstances. So things like your simulated annealings. We do not compare the relative performance of different heuristics. This is really important, and I'll make the point again later. What we're instead doing is that we're just calculating the number of steps per unit time that the quantum computer could execute. Apologies. So the picture is basically this. These heuristic optimizers, you imagine that there's some step that will get you closer to a solution, then you do another step and you're closer, another step you're closer, and another step you're closer. But different heuristics, different steps will take you different distances. Some heuristics will do better in the sense that fewer numbers of steps will take you to a solution. Other heuristics, you might have to take more steps, but each step might be computationally cheaper. And we're not really doing an assessment about what's the overall cost of reaching a solution. We're only giving an assessment of the overall cost of doing a single step in each of these different heuristics. So what that basically means is that the numbers that you see cannot be directly compared between different heuristics. So again, I'll make that point a bit later because it is quite important. Now, given that this is a compilation workshop, I really need to be clear that our backend compilation strategy is extremely crude. So all we're doing is we're taking algorithms, counting the TOEFLs or the CCZs or the T-gates or whatever your preferred non-Clifford gate is, and we're assuming that this is going to be executed with one so-called factory and it's going to be used sequentially. So for those who are aware of how surface code compilation works, then this will make sense. For those who aren't, just imagine that this is an extremely crude way to cost out things. The last point that I'll make, but not the last point that is worth making, is that our comparison to classical is also quite crude, but we're doing it in a way that's charitable to quantum heuristics. So basically what we're doing is we're imagining that the quantum heuristic would require exactly quadratically fewer steps than the classical heuristic. And so we're essentially ignoring any quibbles about constant factors or lower order terms or whatever it is. This is just essentially the back of the envelope that justifies our headline claims in our paper. So with all of that aside, what I'd like to do is I'd like to just give you a sense of how we arrive at these conclusions and what's our process. And you'll notice that this goes from rather detailed to rather less detailed. So again, I want to make this point that the back end, so these last 2 points in the flowchart are quite crude. But this is because we're trying to just get a sense of how well things would work based on what we know about the algorithms. And really our work is about designing the algorithm primitives, which is why I've sort of put it in gold instead of gray. So essentially, in order to come up with these algorithm primitives, or to design them, I should say, we have to do 2 steps, which can happen independently, but they both lead to a lot of complexity, meaning the colloquial sense in terms of how much we have to sweat to get answers. And one of those 2 ways that we have to sweat is in terms of selecting the problem type. So we focused on, this is the list that I've given here is hierarchical in the sense that the top is most general and the bottom is the most specific. So the most general kind of problem that we're considering is we're imagining the combinatorial optimization problem is you can think of it like a Hamiltonian, and you're looking for the ground state of some Hamiltonian. And the idea is that the Hamiltonian is a spin network of some kind, and then the idea is that there's some alignment of spins that's going to be the optimal, and then other ones are going to have higher energy. So the L-term spin model is sort of the most general way you can imagine posing what I've just said, which is just a linear combination of various different tensor products of Pauli Z operators, and the L is just the number of terms in that sum. So that's quite general. Then there's a more specific version that's kind of more interesting in practice, which, well, in the sense that it's a bit more tractable than the L-term spin model. And that's what we're calling the quadratic unconstrained binary optimization problem, QUBO for short, and physicists would probably know this more well as the Ising model. Then there's a specific version of the Ising model that we're calling the Sherrington-Kirkpatrick model, and this is essentially an Ising model with +-1 weights. So no numbers other than +-1 can count as a weight in that Hamiltonian. And then the last one in this list of possible problems we looked at was the low autocorrelation binary sequences. So this is a specific hard case of the SK model. So it's a specific instance. So given what problem type has been chosen, then there's different ways to evaluate the cost function. And then but there's one more ingredient that we need before we know how we're going to try and evaluate the cost function. And that's what strategy we're going to use, what kind of heuristic. So the amplitude amplification heuristic is, if you're not quite sure what that means, essentially it just means something that's kind of Grover-like, and it's quite a simplistic idea. Quantum approximate optimization algorithms, I mean, there's so much to say about that I'm just going to call it QAOA and just move on. Then there's an interesting kind of adiabatic approach that we looked at in this paper. And then we actually looked at several different ways of doing quantum simulated annealing. And I'm going to stress that this is not the same thing as quantum annealing or simulated quantum annealing. What this is you imagine simulated annealing as it would be done on a classical computer, but then you imagine the quantum computer doing that simulating rather than the classical computer. So the description of the algorithm is still sort of inherently classical, whereas for quantum annealing, there's something quantum about that description. And that's what we mean by quantum simulated annealing. So we take these 2 points. We have a problem type and we have a strategy. And once we know these 2 things, then we can design a cost function oracle. So often when you look at, for example, Grover search, it's actually an oracle separation that you prove. And so you have to sort of just have a black box. But we're not going to get away with that for this kind of analysis. We have to actually say, what does it cost to execute these oracles? So there's, roughly speaking, 3 different ones, slightly more accurately 4 different ones. So the most obvious way to implement a cost function is to query the oracle with a candidate solution and then have it write down the cost of that candidate. A variant of this is that you query it with a candidate, and you're also and then it tells you the difference in cost between that candidate and another candidate with exactly 1 bit flipped, and then different oracles for different bits being flipped. So this is the sort of obvious one, and those do come up. Then there are slightly weirder ones. So there's the so-called phase oracle, where the value of the cost function is returned not by writing it down to some other quantum register, but as a global phase to some quantum register. And then there's the LCU, which stands for linear combination of unitaries. And this is when the cost function is essentially executed as a Hamiltonian. And what that means is you take your Hamiltonian and you multiply it directly to a target quantum register. Now, for those who are kind of quick on their feet and also don't know this area, they might think, well, hang on a second, Hamiltonians aren't always unitary. And the way that you implement non-unitary operations on a register is essentially by measuring and post-selecting. And there's quite a lot of clever techniques to do this. So once we've identified those, the kind of cost function that we're using, having already chosen the problem type and the strategy, then we can get down to design the algorithm primitive, and that's where a lot of the work in this paper really is. Then once we design the algorithm primitive, then we take a breather, and then we count the number of Toffelees that algorithm primitive requires. And then to give a crude estimate for like how well an early quantum computer would do, we're just going to multiply by a time cost. And there's a little bit more to it than that. How many physical qubits per logical qubit, and there's actually a slightly more esoteric issue that I'll mention briefly later. But before I get into the actual costing part of this, I just want to give a sense of what goes into this algorithm primitive design part, in case the audience doesn't know. So just to give a sense of what we did in our paper. So this is a partial list of the various innovations we have in our paper during this process of algorithm design. So we managed to find a logarithmic factor reduction in calculating the Hamming weight of a bit string, which ends up being useful in a variety of ways in our paper. We've also come up with an interpolation-based scheme for function evaluation. Now, this is indicated when you don't really care too much about the accuracy of your function. You can, and because these are heuristic optimizations, we're pretty happy to say that accuracy isn't really the primary goal of the function evaluation. You just want something quick and dirty to make the heuristic work. Then a few other, just to sort of complete the laundry list, there's a quadratic improvement to the cost function evaluation in QAOA. There's a new approach to adiabatic optimization. So like kind of glibly put, this is stroboscopic simulation. And there's various methods or even improvements to existing methods for quantum simulated annealing. So and again, just to sort of highlight some of the work that goes into this, I'll just pick on one of these and just explain it a little bit further, but in the interest of time, I'm not going to get into this too much. Again, 77-page paper. So for the interpolation-based function evaluation, what we essentially are, so we need to, for example, calculate a Metropolis-Hastings updates rule if that's the way that we're going to do simulated annealing. And we have to do this on a quantum computer if we're going to do a quantum version of this. And again, it's not really necessary to accurately evaluate what turns out to be an exponential function, or maybe the arcs of an exponential function in the Metropolis-Hastings update. So the idea is that what we did in our paper was to say, instead of trying to evaluate the exponential very exactly, we just look up which region the input is in. So these various orange lines are indicating the lines between the blue dots, and the blue dots say if the input is between the two blue dots, then that tells us what is the slope of the intercept of the linear function we are supposed to evaluate. So the idea is to look up to figure out which of these various regions, read out the answer to another register, and use that information to calculate a linear function. So you know, your slope of the line and your intercept, and then you do a multiplication and an addition, and then you've calculated an approximation to the exponential. And so we introduced a way to do this. It's a variant on an earlier idea that Dominic did with some other people at Google called QROM. That's a very neat trick if you're looking for interesting neat tricks to study in quantum algorithms. And so we've got a variant of it, which is called variable spacing. So the original idea of QROM would require equal spacing between the interpolation points, but we've got a variant where you can look up an exponentially growing spacing between lookup points. Okay, so then we do all of that work and we get just this huge pile of results. So this is just a snapshot of some of the results that we have. There's a couple of tables in our paper, and there's a ton of tables in our paper. These are just two of them. So we do all of this sort of TOEFL counting, and we do all of this analysis to decide what's the overall runtime, and then we make faces like our friend the emoticon down below. And if that's how you feel, then you have to imagine what it was like for us to essentially spend our COVID lockdown doing this. And just to give you a sense of what happened to us during our COVID lockdown while doing this, this is a before and after picture of Dominic. So before this is what he looks like on his website, and this after picture is a picture I took of him just today. So you can get a sense of how much work went into those tables. So I'm going to spare you that a little bit, and I'm going to boil it down to this table over here, which is essentially a summary of a summary. So if you look at table 1 in our paper, there's a summary table, and this is a summary of that summary. So roughly speaking, I'm looking at 4 different algorithm primitives in this table over here. So there's amplitude amplification, QAOA, adiabatic, and simulated annealing. The TOEFL counts you can see, except for the adiabatic, it's a quadratic count. And then you can see that there's sort of these like either order and order log ends. The big O's are often hiding details of the precision to which we're trying to evaluate the outputs of oracles, or the various functions that we're calculating of the oracle outputs. And so I'm just sort of treating them as constant for this table. And I'm also, I should comment, just looking very specifically at the labs problem. And so then we get these numbers that say how many steps of these various different heuristics could the quantum computer execute in one day, right? And this is assuming that the quantum computer has 1 million physical qubits, a 10 to the minus 3 error rate, which tells you about the sort of error correcting code you're supposed to use. And so you can see that the numbers are, well, they're numbers. And I stress again that you can't really compare these different numbers because you don't know whether a step of one algorithm is going to correspond in any meaningful way to a step of another algorithm. But maybe the best way to contextualize these numbers is to point out that the number for simulated annealing, this 1700 number, if I program my laptop with a fairly throwaway piece of Python code to do simulated annealing with Metropolis Hastings, I can do that many steps in a half a second. So these are not encouraging numbers for optimization, is essentially the point there. Okay, so I'm pretty sure that I'm getting close to the end of time, and so that means that it's probably a good idea to reach some conclusions and then answer some questions, of which either there are many or there will be stunned silence. It's hard to know which. So in order to really bang the point home, I just want to say that it really does look like that quadratic speedups are insufficient for quantum computers to beat classical computers, or at very least early quantum computers. Now, of course, because it's a quadratic speedup, sooner or later you build a large enough quantum computer, and sooner or later it's going to beat a classical computer, because that's how asymptotics work. But the point of this study is really not about asymptotics. It's about saying what happens if you have this 1 million qubit machine of the kind that Google's sort of trying to build. So if that's depressing to you, then I can offer the following possible ways forward. So you could try to lower the hardware noise, and with all due respect, good luck with that. You could also try to come up with better error correction methods. With all due respect, good luck with that. You could also try to build bigger quantum computers. So like we're talking much more than 1 million qubits pretty clearly. With all due respect, best of luck with that. And then there's also you could also try to find better than quadratic speedups for optimization algorithms. And with all due respect, good luck with that. The fifth way forward is you can sort of accept, as I have, that maybe early quantum computers just won't be that useful for optimization. Maybe we just need to be setting our sights higher in terms of the size of the quantum computer that's going to be useful. And with that, I'll close off and welcome questions. Thanks for your attention.
thanks for the talk.
Cheers.
We check. So, I haven't received any question yet, but let me ask you a question. So maybe with respect to the still like getting over the picture you showed.
Which picture was that?
Dominic.
Oh, yeah, like, yeah. I'll just sort of leave it there. Yeah, sure.
But the last slide was pretty pessimistic.
This one here, you mean? Mm-hmm.
No, the last 5 points that you have, like except for the last.
Oh, this one. Yeah. I'm being pretty pessimistic. That's true.
Mm-hmm. If you could give me a bit more optimistic. So, what do you think of these?
Well, okay. So, yeah, sure. I can definitely find ways to be more optimistic. So, So first off, optimization isn't the only thing we might be doing with a quantum computer. That's really the thing to remember. So we were looking at a very specific potential use case, which is combinatorial optimization. We were looking at very specific heuristic optimizers, and okay, there's actually there's quite a bit I can go into here. So I'll just so probably the biggest one is just that, yeah, optimization is not the only use case of a quantum computer. But let's assume that we're only asking about a quantum computer for doing optimization. Then the other thing is that, look, we don't know if 1,000,000 qubits is big or small. So when my laptop is beating this, remember that my laptop has way more than 1,000,000 bits. So it's kind of not a fair fight. Now, that's not necessarily going to be an optimistic story, but it's just that classical computers at some point have, many decades of a technological head start here. So we shouldn't be too surprised to find this out. But even let's say that we're trying to get a 1,000,000 qubit quantum computer to beat my laptop, and let alone a supercomputer. And then the thing to remember is, and then let's assume that we're not doing lower hardware noise or better error correction or whatever else. So the story that I would really offer is that when we talk about the idea that we don't know how, we can't really compare different steps of different heuristics, we need to take that a bit more seriously. So we intentionally didn't do this for this paper because it would have turned the paper into like, thousands of pages or something. But the idea is that when, for example, you look at simulated annealing, it's not, the thing that you're doing in the simulated annealing is not simply to prepare a Gibbs distribution. You're preparing this sort of coherent Gibbs state where the amplitudes are like the square root of the probabilities. And so it may be the case that you also need fewer, the quadratic speedup comes from this idea that you need fewer steps to get to a thermalization. But there might be all sorts of subtle ways in which the different parameters in the heuristic are playing with each other. And there might be a lot of work to do just to find out how well these heuristics are doing. Like this is, again, a very crude analysis, and a better analysis might actually show us that quantum computers are doing much better than it looks like from these numbers. Another comment is just that our compilation strategy is so crude that you shouldn't take it too seriously, just as sort of a ballpark figure. And maybe cleverer compilation strategies will find you, constant factor speedups that make this look much more enticing.
Okay, thanks for this outlook. And I see no further questions so far, but if there are more questions, then we can ask them in the Slack channel. So thanks again.
Yeah, so I'll be checking in on the Slack, and I'll be checking in throughout the day. So well, the evening, yeah, so it's evening here, so I'm probably going to go home soon, and then but I'll be watching the Slack for questions.
Okay, great. Thanks a lot. Good evening.
All right, thank you.
Bye.